Hello, I'm Nadav Amit, and today I'm going to present our recent work on TLB shootdowns, a joint work with Amit and Michael Way. This work revolves the translation look-aside buffer, or TLB. As you know, CPUs and operating systems use virtual memory, and the CPU translates memory addresses from virtual to physical ones before it performs memory accesses. Virtual memory allows to provide each process an isolated address space and to provide services such as memory deduplication. The prevailing data structure that CPUs use to hold these virtual to physical address translations is a radix tree. If the CPU needed to traverse the page tables to translate every memory access, it would incur unreasonable overhead. To avoid this overhead, the CPU caches in a dedicated cache the radix tree leaves, which are known as the page table entries or PTEs. This cache is the TLB. While the TLB is basically a cache, it is an incoherent one. Changing a PTE in memory is not reflected in the caches, and flushing it requires an explicit invalidation instruction to be used in most architectures. Invalidation of PTEs in remote TLBs is not supported in many architectures and requires software, the operating system, to restore coherency using a protocol which is known as TLB shootdown. This slide describes how TLB shootdowns are performed. The operating system thread that updates a PTE does not know which CPUs cache the PTE. It can invalidate the relevant entries in the local TLB directly using a TLB flashing instruction. Yet in x86 CPUs and others, it cannot flush remote TLBs of other CPUs in this manner. Instead, the initiator sends an interprocessor interrupt, marked here as IPI, to the responder course, the course that might hold the stale translation, and asks them to invalidate their TLBs. The responders receive the request, flush the TLBs, and acknowledge the initiator that coherency was restored. Only then the core that initiated that invalidation continues execution. TLB shootdowns are expensive. In this work, we try to see how we can optimize the way they are performed without introducing dramatic changes to the way operating systems work. We therefore looked at the way that Linux performs TLB flashes of user space mappings, which are the common case. The lessons we learned are relevant to other operating systems as well. TLB shootdowns are not new, and there are many existing solutions, which would not fit into this slide. Most of the proposed solutions delegate the remote TLB invalidation task to the hardware. Such hardware, however, is not available on all architectures, and even when it is available, the hardware interfaces are not always suitable. For instance, on ARM, the hardware can flash remote TLBs, but this is done through broadcast to all cores, which results in high overhead on big machines. Several software solutions were proposed as well. The notable ones are page table replication, which was introduced in Radix VM. This solution requires extensive operating system changes and is not likely to work well when IPI latency is not very high. Another solution is aggressive batching, as proposed by LATR. This solution breaks POSIX semantics and might affect security and robustness. Let's discuss the solutions that we propose and start by looking again at the way TLB flashes are performed. In both Linux and FreeBSD, we see that precious CPU cycles are wasted in the initiator while it waits for acknowledgement from the responders. These cycles can be used for flushing the local TLB in the initiator. We therefore move the TLB flush to that busy wait period. It turns out that that benefit of performing concurrent flashes was realized over 30 years ago by Rosenberg. However, this lesson was apparently forgotten. Now, to understand the next optimizations, let's have a deeper look into the way a TLB showdown is performed by the responder in Linux. Three operating system components take part in the showdown: entry code, SMP code, and TLB specific code. When an API is received, the entry code performs a lightweight context switch and calls the SMP handler. Nowadays, due to the Meltdown vulnerability, the kernel also loads a different kernel address space as part of the page table isolation mitigation. The SMP handler then reads the request and invokes the specific API handling routine, which is the TLB flashing routine in our case. The flashing routine reads the detailed shootdown request that the initiator sent and performs two flash operations, one for the kernel page tables and one for the user page tables, as required for page table isolation. Once the TLB flashing routine completes, the responder acknowledges the SMP request, and eventually the kernel returns to user space. When page table isolation is enabled, the kernel reloads the user page tables at this point. While sending the API is the most expensive interaction between the cores, there are additional interactions. The initiator and the responder communicate through shared memory. This communication is wasteful. The SMP and the TLB components have different data structures, which are located on different cache lines. In fact, the shootdown request information was allocated on the stack, which might be misaligned and cause TLB misses. Once the problem is understood, the solution is straightforward. Collocate the TLB information with the SMP request. Next, let's look at the responder acknowledgement. As we saw, the initiator will be idle until the receiver acknowledged itself the TLB flashing request. This raises the question, can we acknowledge the TLB shootdown before it was performed? This might sound wrong, but as the kernel is not going to use any of the page table mappings that are about to be flashed, there is no harm in doing so. The shootdown initiator would therefore complete flashing faster with no negative effect on the receiver. We therefore perform what we call early acknowledgement. We acknowledge that the TLB shootdown request was completed before flashing actually took place. This is safe and allows the initiator to complete the shootdown faster. Now let's focus on the flashing of the user page tables, which is required due to the page table isolation. Currently, Linux flashes individual page table entries of the user page tables right after it flashes the kernel table. It turns out that flashing the entries in the user table is more expensive on Intel CPUs than flashing the kernel table entries, as the operating system needs to flash page table entries in a different address space, and the instructions that does so in PCID is slower. Instead, we can perform in-context flashes, defer the user table flash so it would be performed later, after the user page table is already loaded. Doing so provides two benefits. First, it allows us to use the faster TLB flashing instruction. Second, if many TLB flashes are required, we can just fall back to do a full TLB flash, as in such a scenario, it would be more efficient. In the paper, you will find an additional optimization, user space safe batching, which defers all TLB shootdowns while the kernel runs. You will also find an optimization that avoids TLB flashes on copy and write, and some interesting effects of page size mismatch on TLB flashes in virtual machines. I also skipped many important and subtle details in this talk. For evaluation, we created a micro benchmark to measure the time that is spent in the kernel by the initiator and the responder when one thread calls madvice.need to unmap 10 pages. Both threads record the number of cycles that were spent in the kernel. We show the results for the initiator on the left and the responder on the right when they are located on different threads on the same core, on the same socket, and on two different sockets. We show the performance of the baseline system and when each optimization is added on top of the previous one. As shown, the concurrent TLB flashing optimization provides the greatest benefit for the initiator, as it cuts the TLB shootdown time almost by half. Cache line optimizations have a small, roughly 100 cycles benefit for both the initiator and the responder. Early ACK benefits only the initiator, allowing it to finish the shootdown earlier. When early ACK is applied on top of concurrent flashes, Its benefit is mostly in avoiding the overhead of the interprocessor communication. Finally, the in-context optimization benefits any TLB flash, even those that are not related to TLB shootdown, and saves roughly 100 cycles per flashed PTE. To measure the benefit on workloads, we use the sysbench benchmark, which performs random writes to memory mapped files and periodically flushes the writes, triggering TLB shootdowns. We run the benchmark on emulated persistent memory with no write cache. We measure performance when the benchmark is run with different number of threads each time and show the speedup. We can see that the effect of the cache line consolidation is more apparent here as a shootdown of a single PTE is performed each time. We can also see that early ACK does not provide benefit when the number of threads is high, which seems to be related to the fact that multiple multicast IPIs are required in such case. The blue line shows the speedup when we defer all TLB shootdowns while the kernel is running. There are various anomalies that we explain in the paper, and we think can be avoided by some tuning. Eventually, we get a performance improvement of up to 22% with user space, safe batching, and 11% without. To conclude, TLB shootdowns can be improved with relatively simple changes. Performing TLB shootdowns in hardware might be the ultimate solution, but doing it well in software would allow to design the right hardware interfaces. We are working on pushing these enhancements to Linux, which was somewhat delayed, but would hopefully be finished soon.